There we go. Okay, we're good. Is a brief descriptive coefficients that summarize a given data set. Inferential is a sample subgroups used to conclude information on a population. Ultimately, that may or may not make sense to you as it's written. The way I like to look at this is descriptive are basically your numbers. What did you collect? What information did you collect? Inferential is going to be, how do I use that to answer a question? I look at that data and I decide, how does that answer a particular question? Because anytime you're using statistics, you're trying to answer a question. So when you're talking about descriptive, the first thing we've already covered with descriptive includes your mean, median, and mode. We already did a whole bunch of descriptive stuff. Our mean, median, and mode. What I might do is I might figure out what is the average height in this classroom. That means I might take the mean or the median. That would be a number. It's a number that's applied to your given heights. Now, that would be our descriptive. What our inferential would be based upon that is I might use that to answer the question, what's the average height of a geometry student at BA? So I might take an average of just this class, which would then apply it to a population, all geometry students. So inferential typically takes a sample and applies it to a population. Now, I do want to point out that population does not mean Earth's population. Geometry students at BA can be a population. That's the only people I'm looking at. So if I measure the heights in this class, I could say, okay, our average height is, 5'1". And then I would say, okay, the average geometry student is 5'1". I just have to measure this class because you are the sample size. You might be a random sample because you randomly got placed into this classroom. So the number would be descriptive. How I use that number will be my inferential. How do I use it to answer a question? Now, some more things that we have descriptive. Today we're going to start filling out charts. We're going to talk about bar charts today. We've also already done box plots. Tomorrow we're going to talk about histograms. Then we're going to get to line charts. These are different ways that I take numbers and it's just so I can visualize what those numbers look like. Doesn't mean it's inferential. I'm just taking data and I'm plugging it onto a chart. Still data. How I read that chart then would be inferential. So if you had something that, maybe a bar graph that consistently goes up, I can then predict something's going to continue to go up. That would be inferential. Some more things that would happen in descriptive, which we don't know probably, is standard deviation. We'll learn about that later. Standard deviation slash, let's go variance. Standard deviation and variance are basically just testing your variability of our data. What I mean by variability, the bigger the standard deviation is, and we'll learn this later on, the more variability there is with our data. So think about this classroom right here. If I measured all of your heights would all be kind of close together. It would have small variability. However, if I compared your heights to, kindergartners up the hill, there's going to be a lot of variability between you and their heights. There's going to be a vast difference between tall and short. That would have a big standard deviation. So the bigger this number is, the more variability there is. But once again, we'll have a whole lesson where we talk about standard deviation, so you don't have to worry about that. All right, so descriptive are our numbers, they are our charts. Inferentials, how do I apply that information to a population? In order to do that, a lot of times we'll use something called probability. To say, now the bigger your sample is, the more likely you are to be able to say this affects our whole population. If I would do this entire classroom, I'd probably be much better off than if I picked two of you and measured you two, took your average height and said you are the average height of a geometry student at BA. If I just take 2 people and that's my sample size, it has a low probability of being correct. The more people I take, the higher that probability is. And when you're doing statistics, a lot of times you actually have to say, how accurate are these results? A very key way that you see all the time, if you follow politics at all, when they do those little polls of who people are going to vote for, they actually say how accurate these polls are, and they give you like a plus or minus of a certain amount. So probability often deals with inferential, and the next thing that often deals with it is a hypothesis. Hypothesis. What do I think is going to happen? And then I collect statistics and see if that hypothesis is true. My hypothesis was that the average student height in geometry is 5'1". I would measure a whole bunch of random people, and I would see if that hypothesis is true. And then I would say, well, this is my amount of probability I have that that hypothesis is true. So we can never say 100% unless you measure everyone in your population. So you'd say, all right, I have like a 95% chance that you're about 5'1". All right, so that's the big difference between descriptive and inferential. Know the difference. Descriptive and inferential. Now, when we're collecting data, there's 2 big variables that we can use, and that's the measurement that may change from one item to the next. So the first big thing we need to talk about are categorical, and then we'll talk about numerical. Categorical is also called qualitative. You have to know both of these terms. Categorical equals qualitative. Once again, categorical is qualitative. Well, categorical makes sense, because if you picture categories, that's where categories comes from that categorical. Are values that are names or labels. Think about the color of a ball. It's either red, blue, something. It falls into these neat little bins. Or think of a breed of dog. A collie, a shepherd, a terrier would be good examples of categorical variables. It's a name or a label for a group of things. The next thing is numerical or quantitative. Variables are numbers. For example, when we speak of the population of a city, we are talking about the number of people in this city. Now, here's the thing you need to pay attention. In order to be numerical, it doesn't just mean you use a number. It has to be a measurable attribute. It has to be a measurable attribute to be a numerical representation. Therefore, populations would be a quantitative variable. Numerical variables can also be described as discrete or continuous. Now, let's talk about the difference between discrete and continuous. Discrete is a variable that can only take on a certain number of values. Continuous are variables that have infinite number of possible values between. So I always like to think of a number line when I think of discrete versus continuous. So I'm just going to draw a number line real quick. In order to be discrete, and we'll go over some examples if this doesn't quite make sense. To be discrete, there has to be a way that we have to pick up our pencil to label these. So let's picture this number line is 10, 11, 12, 13. If I was giving a particular age, if I was saying my particular age, and I'm either 10, 11, 12, or 13, I'm only going to pick one of those numbers. I'm going to pick 10, 11, 12, or 13. Now, you might say, Mr. Pabian, I know I'm not exactly 12. I'm actually 12.73 years, but no one ever says that. If I ask your age, you're never going to say it's 12.73. You are going to pick one of these, and it's almost like categories. It's almost categorical, but it is represented by numbers. Now, that would be discrete because I can either be 10, 11, 12, or 13. Now, let's turn this into continuous. Let's say I'm weighing an object that weighs between 10 and 13 pounds, and I have a standard scale. Now, as I measure it, the scale goes up and down. It can cover all of those numbers in between. I can say this particular thing weighs 10.45 pounds. It covers all that stuff in between. Your standard scale has a thing that goes in between all of those. That would be called continuous because we can have all those decimals in between will work. So let's look at those two examples I just did. For discrete, I said age. I'm going to circle age in just a second. I'm going to circle that for a second. And then for continuous, I used weight. And those are the two big ones I had, yeah. I circled age because people can make an argument that it is continuous. That you might say, I am 12.734 years old. So if you're that person, you can put in continuous. But I think most of us, age is age a year specific. It is you are 12, you are 13, you are 14. Does that make sense, why I put it into there? All right, can anyone think of something else that would be discrete? That would be numerical. So we measure it, but it is discrete. Rigo? Height. So is there any in between? Are you either...
Well, it's like the same thing as... Well, yeah.
Would it be the same thing as weight, though?
Not really.
Not really?
Nobody says they're like 6.7.
Do you think your doctor does?
No.
No?
He just says like, I'm 5'6".
Well, when they take your height, right, you stand against the wall, and they put that little thing on there, can it be anything between those heights?
Yeah.
Yeah, so it would actually be continuous. If you're listening, if I say, so if I would say height, give me height to the nearest inch, then it would be discrete because we only can go, 60 inches, 61 inches. But height is more often considered continuous just because when you walk up to that wall, that they do to the nearest, whether you know it or not, your doctor does it to the nearest. So I would, just for the sake of this, just put height in the continuous. Yeah, Augie.
I was going to say population.
Population? Yeah. Because either you have 1,043,000 people or you have 1,042,000 people. You don't have a partial person. Grace?
Well, any number of people or animals, because you can have part of a person.
Sure. We can counting animals, maybe pets.
Yeah.
Number of pets. Yeah.
Would anything that you can't do fractions or decimals for be discrete?
Yeah.
Okay.
That's a good way to think about it when you don't have to. Sometimes fractions can be discrete though, because we could, as long as it's just halves or something like that. Yeah.
Like a record of wins and losses.
Wins, losses. Yeah. Number of, let's just put wins. Now remember, your wins could be considered half as well. You can win 2.5 because you can tie, and a lot of things call it as a half. That still makes it discrete because you can't be 12.23 kind of thing. It's not continuous. All right, and examples like this. I think an easy way to know for a fact that it's discrete is if I can't use any decimals, it has to be discrete. We have weight and height as continuous. Can anyone think of anything else that might be continuous? Yeah. Maybe time. If you're timing how long it takes to do something, or if you're timing a race, yeah.
Amount of money spent.
Amount of money spent. Amount of money might be discrete because the smallest thing you can have is a penny. You can't pay fractional a penny. So you could maybe argue it. Maybe you can have partial. Because when you buy gas, it's a certain fraction that it costs. But more often than not, it would be discrete just because that is that smallest unit that we'd have to go to. But time is a great one. Like if you're running track and they give you a time, you can go anywhere. They're not going to say, oh, you guys both tied because you finished within the same minute of each other. You go to thousandths of a second to delineate between who's winning or losing. I think that's a good start between discrete and continuous. There is gray area between all of these because time can be, if I just give you 2 hours to do something, that is definitely discrete because you only have 2 hours. There's nothing in between. So if you're on a test and you're not sure, just elaborate on why you think it's discrete or it is continuous. On the test, I try to pick ones that are pretty obviously one or the other. But if you have an argument, make it on the test. All right, questions on discrete or continuous? Then let's check out if we understood it. All right, we have to label each of these as categorical or numerical. If it's numerical, state whether it is discrete or continuous. So once again, if it says numerical, you then have to say discrete or continuous. The number of phone calls received in a day. First of all, is it numerical or is it categorical? Anna? It is numerical, which means we have to go one step further. Is it going to be discrete or continuous, Rigo?
Discrete.
It will be discrete. If we kind of picture that number line, I would have 10, 11, 12, or 13 phone calls. I'm not going to scale the stuff in between. So it would be numerical and discrete. All right, eye color. Is that numerical or categorical? Yeah. Categorical. Let's put cat. Cat eyes. Could someone make this numerical? And there is a way. There's actually a few ways. But there's one way I'm thinking about it. Yeah.
If you like have categories for each eye color, you gotta set. You had like.
Still categorical, though. Because you just said I'm going to make categories for each eye. Yeah.
You need to assign the colors numbers so you can, like, you know, paint's identified as like really weird.
Yeah.
Like BTF4 or whatever.
Yes. So if you're into programming at all, you don't select a color. You actually measure it by a number. It tells you how much red, blue, or green is in something. And in those cases, that would be numerical. Do we normally do that? No, if I ask your eye color, I'm not saying, are you a 231 or a 233? You're going to say, no, it's like blue, green. Like, okay, so they're categorical. We're going to stick with categorical. I'm just going to show you that in some fields, we could count it as we measure a certain number as follows. All right, number of Instagram followers. Numerical or categorical? It is numerical. Well, if it's numerical, then we have to decide. Let's just put num. Is it going to be discrete or continuous?
Discrete.
It is also discrete. Let's put num disk. It's a num disk. Weight, numerical or categorical? Anna? Numerical. Is it discrete or is it continuous most of the time? It is usually continuous. Zip code. Zip code. Rigo.
I would say categorical.
You would say categorical. Why not new? Doesn't it use numbers?
Yeah.
Why is it categorical? I agree. Do you know why?
Assigns to the house and then giving the house a label.
It's just a label. You're giving something a label. That's a perfect. This is the first time both my geometry classes got this right. It is categorical. It uses numbers, but the number is just giving a name to something. 53213 does not say how many people are in Wauwatosa. It's just a name given to Wauwatosa that we put on letters. It is a label. So that's great. All right, 40-meter dash time, numerical or did I just say numerical or categorical? Camden?
Numerical.
Numerical, is that discrete or is that continuous?
Continuous.
It is continuous. I think at your homework you have to label a whole bunch of them as discrete or, it's categorical and numerical. All right, we're going to talk about two graphs today. The first graph is called a bar chart. Be careful with a bar chart because tomorrow we're going to talk about histograms. Histograms will look a lot like a bar chart, but they're going to have a big key difference. Bar charts use only categorical variables. Categorical variables. So if I say bar chart, you're going to think of two things. Categorical and the next thing you're going to think of are gaps. You mostly never push these together. Our histograms we're going to push together and we'll use numerical data. So this is going to use categorical data, and we're going to leave gaps between the different categories. Now, we're going to do an example together. And because bar graphs kind of, they show you how things are kind of blurred a little bit in statistics. We're going to do a bar graph together where we're going to count the number of pets we have in this particular class. So we're going to see how many people have dogs. If I could pull up the right tool, we'll see how many people have dogs. We're going to see how many people have cats. Maybe we'll do birds. And maybe we'll do other as a catch-all. Are dogs, cats, birds, or other categorical data? Yeah. We're going to count how many people have it, so a lot of people are like, oh, that automatically changes to numerical. That is not what it means. In statistics, you're always tracking how many people are affected by this. So you'll always have what's called a frequency. How many times does this happen? That does not switch this from categorical to numerical. You just look at your x-axis, are dogs, cats, birds, and other categorical. This is a categorical subject. Then we just got to figure out how many people have it. So let's go ahead and label this as pets, I guess, in this classroom. And let's figure out how many we have. How many people in this classroom have dogs, or at least a dog? 1, 2, 3, 4, 5, 6. Did I miss anyone? 6? 1, 2, 3, 4, 5, 6. Okay, so we have 6 people. So we should have our scale go at least to 6. Leave myself a little bit of room. 2, 4, 6. So we'll draw a little chart that goes up here. How many people in here have cats? Or a cat? 1, 2, 3. 3? How many have birds? How many have other? That could include fish or, 1, 2, 3, 4. So we have 4. Now, obviously, the bottom would be kind of type of animal. I'm just going to put type. Now, that 2, 4, 6, that's going to be what's called our frequency, our number that it occurs. That'll be a new word that is our frequency. How often does it occur? It's hard to write sideways. Frequency. How often does it happen? Well, 6 people in this room have a dog. That's called our frequency. And this is definitely going to be a bar chart. We have gaps. We have categorical data, so that is a bar chart. Once again, tomorrow we're going to talk about histograms. Those will be numerical, and they will not have gaps. It's the easy way to tell between the two. All right, the last thing we're going to talk about today are stem and leaf plot. A stem and leaf plot are kind of a way to form a bar chart of sorts. It makes it go sideways, and we can see all of the data at once. So I don't have to raise it up. This is actually a way to list all of our information in order and give us a nice little chart to see where it's like we have our maximum values and stuff. So if we look at every one of these, we have a stem and we have a leaf. They combine to make one data point. So if we look here, we're talking about test scores. Someone here got a 66 on a test. Then if we go to the next row, someone got a 70, a 75, a 77, a 78. Someone had an 84, someone had a 99, someone had a 100. A stem and leaf plot, now you might want to write this down, needs a key. To get these correct on the test, it needs to have a key. I need to see one of the values. So if you look here, we have a 92 equals 92 points. Let's pretend I didn't say there's 18 students. What would you count to figure out how many students took this test? Yeah. How many numbers are on the leaf side? So the leaf side is going to be our numbers. So if you count the leaves, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Ooh, 18. Matches up with what they said. So we can go ahead and say we have an n equals 18. Let's say I was told to find the median. It's set up for us to find the median. How would I find the median of this? Shouldn't be confused. We should think about this. Yeah.
You go like 9.5 in
We would go, where'd you get 9.5 from?
18 plus 1 divided by 2.
18 plus 1 divided by 2. So we could still find our center. Our center would be n, which is 18, plus 1 divided by 2, which equals 9.5, which means we're going to count in. Does that mean my median is 9.5? No. It means count 9.5. So I'll actually do that. I'll go 1, 2, 3, 4, 5, 6, 7, 8, 9. 9.5 would be smack dab between 4 and 4. What's between 4 and 4? 4. Does that mean my median is 4? No is correct. What is our median? Anna. It would be 84. You have to be careful with these. That's why we always have a key. And we can say this right here. Questions on that? Yeah. Yeah, go ahead. All right, our next one is pretty standard compared to this one. We have the heart rates of some patients. I guess I didn't give myself enough space on that one. We have our heart rates of patients. We can see that counting by tens would be good for our STEM because I go from 4 all the way to 8. So what I'm going to do is I'm going to start setting up my stem and leaf plot. I'm going to give you a little hint. For stem and leaf, you don't have to label them as stem and leaf. Notice over here I actually use the word stem and leaf. You don't need that. You just need a T-chart. You need a T-chart that has basically some kind of title, heart rate, we could put beats per minute after that. And then we need to pick something that's going to work for us in our STEM portion. Well, it looks like we go from 4 all the way to 8. That seems like a good STEM. I'll talk about times when it's not a good STEM. So we'll just write down 4, 5, 6. We should really not skip numbers, 7 and 8. So let's say I didn't see any 5s up there. I still got to write it down. You write your lowest number to your highest number, counting all of them, because you have to see if there's data missing. We don't have a lot of data, but I'm going to give you a hint that you'll get this correct more often than not. My advice is circle all of the ones that have 4 in the tens place. So I'm going to circle all the ones that have 4s in them. There's one here. That seems to be the only one, so I'm just going to go ahead and write 45. And after I write it, I'm going to cross it out. Because you're going to find when we have big data sets, you're going to forget about one and you'll have to insert it. Realize if you didn't cross something out, you forgot to put it in, you need to put it in your table. All right, the next thing is we have 5, so I'd circle all the ones that have 5s. We have a 56, a 59. That looks like all of them. As soon as I write down my 56, I'll cross that one out. Then I'll write my 59 and cross that one out. Ooh, did I miss any?
Yeah.
And I'll know I missed it because I'll come across here and go, oh, there was another 52. I didn't circle it, nor did I cross it out. So I need to be able to plug that in. So 52, so I need to have 2, 6, 9. So that's an easy way to catch your mistakes. Now I'll have 2, 6, 9. Now I can cross it out. Now if I see any other 50s, I got them all. Now we're going to go to 6s. We have a 60, a 62, a 60, a 65, a 67. That looks like all of them. My lowest one is 60. I cross out 160. Let's put the next 60 down. Then we have a 2. Cross out 62. Then we have a 5. Then we have a 7. And now I just have 3 numbers left. Those I really don't have to cross out. I just have a 79, I have an 82, and an 83. Now I have a title. The only thing I'm missing is a key. Our key for this one, pick out any value that works that's on here. So I'll pick the 4 and the 5, put 4 bar 5, and just say that equals 45. And I guess we could put beats per minute if you want to make a complete key. That key is important because it will not always be a tens place. If we look at our next example, the common mistake people are going to make on the next example is they're going to make their stem a 3. A 3 would not make any sense. So let's look at that next example. We have 3.26, 3.28. If I just had a stem with 3, picture that. If I had a stem with 3, I would have 26, 28, 34, 38, 41, 42, 44, 50. There's no point in having a stem and leaf plot if I just have one line. That doesn't make any sense. So what we're going to do instead is we're actually going to change that 3 to a 32. Because now I'll have a 32 and a 6. I can have 32, 33, 34, 35, 36 will be my stems. Yeah.
You do 3.2 and
Typically you don't. Typically you use whole numbers. That's why you have that key. So I have 33, 34, 35. And does it go to 36? It does go to 36. Now my leaf could be 32, ends with 6. We had 3.26. Then we have 3.28. Then we switch to 3.3. So we have 3.34, 3.38, 3.41, 3.42, 3.44, 3.59, 3.63. I don't have a title put out there, but I need to do a key. My key will now have one of these values. I usually just pick the first one. 32 bar 6 equals 3.26. Your job when you do a stem and leaf plot is to spread out the data enough that you can actually see something happen. What's the median? I'm going to add median to this one. Let's all calculate the median real quick. Augie, what'd you get for the median?
3.41.
3.41? Anyone agree with that? Yeah, it is 3.41. We could have came up with our center. Our center would be 9 plus 1 divided by 2 would be 5. So we could have just done 1, 2, 3, 4, 5. Yeah, 3.41 would work. Does anyone do that method where you just put your fingers on each end and kind of count your way in? That works. That's fine when you have a small set of data. So what basically happens is you're just kind of crossing out towards the middle. And we ended up at that one. Same thing with your fingers counting inwards. I do that. I do that when it's super small like this. I just kind of finger my way in. It is nice to be able to come up with that central point, because that central point goes really quick when you have a whole bunch of data. All right, we're going to go ahead and skip the next one. I think we've done enough examples with stem and leaf plot. You understand what we do. What I would want to talk about here, would we use 1 as our stem on the next one? Would I use 1 as my stem? What would I use instead for my first stem, I guess? Yeah, we would use 10 because we do have a 103, so we would have to have 10. And then we would just count up until we get to, is it 19? Nope, we got a 20, all the way up to 20, so we'd have 10 to 20. Realistically, you're not supposed to, because you'd like to see where there is gaps of information. You want to show as much information as you can. Kind of like, I think a good example is for pets. If I set up a survey that had birds on it, I can't just, oh, no one had it, so I'm going to erase it. Same thing there. I want to see where there are zeros. So you try not to skip it. Obviously, there are cases where it's just extreme stuff, where it's like 10 all the way to 100. Just wouldn't make sense to have it down, so we skip some. All right, questions on stem and leaf or the old bar charts. Don't forget to study the terms qualitative and quantitative. So my advice is when you're thinking categorical or numerical, go back to this and make sure you know these two words. They usually show up on the test. So you have to know that qualitative is categorical and quantitative is numerical. I usually just remember that quantitative is numerical, like a quantity. You're counting how much of something you have. So quantitative, if I can see these two words together, I always know that qualitative is going to be my categorical. because I know where quantitative goes. All right, otherwise, the rest of the time is for you to work.